Warm greetings to the viewers of this midterm review. I hope you all are keeping safe given the situation of the pandemic. My name is Kabir, and I'm currently pursuing an IDDD in quantum science. I'd like to start by thanking the Department of Engineering Design for adapting with this new IDDD and letting me pursue an internship in quantum science. I'd like to thank Professor Anil from the electrical department who helped me procure this internship, and also my mentors at Bosch who are currently mentoring my project, NISQ algorithms for industrial applications. Before I get into my project, I'd like to take a while to explain the basics of quantum computing, since this is not a core ED subject. The story of quantum computing starts with 1982, Feynman's 1982 paper titled Simulating Physics with Computers, in which he states that since nature is quantum mechanical, we better use a quantum computer in order to simulate it. Cut to the 1990s, you already have three algorithms, namely Deutsch-Schulze algorithm, the Shor's algorithm, and the Grover's algorithm. They either give you an exponential or at least a quadratic speedup over the best classical algorithms. So these are the scientists who propose those algorithms. So this begs the question as to why or how rather the quantum algorithms are able to show this theoretical supremacy over classical algorithms. So the reason for this lies in two principles of quantum mechanics, namely superposition and entanglement. Superposition is a property of quantum systems by virtue of which they exist in a combination of possible basis states of the system. For example, a qubit, a quantum analog of a classical bit, can exist in a state of 0 and 1 like the classical bit, but it can also exist in a combination of states of zeros and ones. So this block sphere on the right, and so once you make a measurement on that qubit, you either get a 0 or 1 with a certain probability. So if you pay attention to the block sphere on the right, each point on that block sphere represents a certain probability distribution of the zeros and ones that you can get along with the phase. We have entanglement, and moving on, we have entanglement. This is another peculiar quantum mechanical property. So you can generate quantum composite entangled systems in the lab. And the peculiarity of these systems is that you can describe these systems as a whole, but individual components of these systems cannot be described quantum mechanically. So this is a very sort of weird phenomena that is only observed in quantum mechanics, and nobody knows how it works. But quantum algorithms have been able to exploit entanglement time and again in order to achieve speedups. So, cut to 20 years later, we have certain quantum computers that have been built by companies like IBM, Google, and Honeywell, but they are seriously limited by a few challenges. The main challenge that limits these quantum computers is decoherence, wherein you lose information that you can extract from the quantum system due to its coupling with the environment and the noise. So the coherence time of today's quantum bits is of the order of microseconds, and that is way less of a time in order to extract a lot or do a lot of quantum computation. So due to decoherence, we are also limited in the number of qubits we can handle at a time, and so our systems are limited to around 50 to 100 qubits. I think IBM has a 65 qubit quantum computer, and Google has a 53 one. So you see the limits are still rather low, but we have to work with what we have got. And so for this reason, we over the past 10 years, we have the researchers have come up with algorithms that are tailored towards these noisy intermediate scale quantum computers, or NISQ quantum computers. Most of these NISQ quantum computers are variational in nature or are called variational quantum algorithms. There are other sort of NISQ algorithms, but variational quantum algorithms form the bulk of them. These NISQ algorithms work best with the current day noisy intermediate scale quantum computers that we have. And some examples of these NISQ algorithms are QAOA and VQE. So the basic premise of these NISQ algorithms, or variational algorithms rather, is that you start with a quantum circuit, a parameterized quantum circuit, and then you run this quantum circuit and finally make a measurement of your cost function. The cost function you would derive from the problem at hand. Once you measure this cost function, you outsource the optimization procedure to the classical computer, and a classical computer tweaks those parameters and sends those parameters back to the quantum circuit, and the quantum circuit runs it and measures the cost again. So if you do this iteratively, you optimize towards to the minimum or the maximum cost, and by getting certain parameters. So as you can see, a part of this is a classical and a part of this is quantum, and sort of a quantum classical hybrid. This is because we do not have a lot of time to do quantum operations due to decoherence, and so we have to outsource some part of it to the classical computers. So in the decades, past decade, there has been a search for quantum algorithms or problems in which these quantum algorithms work and offer quantum advantage over classical algorithms. That's the big picture goal. But more near-term goal that we have now currently is to at least perform as well as the classical algorithms out there. That itself is a promising start for us. So I'd like to elaborate on QA/OA a little more, because this is one of the most promising NISQ algorithms for quantum advantage, and is also one of the algorithms that I'll be working with a lot. So in QA/OA, you have a circuit ansatz, or the quantum circuit, it's a basic subroutine that is run in the quantum circuit. So in the circuit ansatz, you have cost and mixer Hamiltonians. The cost Hamiltonians you get from your problem, and the mixer Hamiltonian is more or less defined, but can be tweaked a little. So you layer these cost and mixer Hamiltonians over and over again to build your quantum circuit that I spoke about, the variational quantum circuit, the parameterized quantum circuit. And then you measure the cost function, and then you train this to optimize this cost function using a classical computer. The classical computer typically runs gradient descent based optimizers for QA/OA, but you can also use other optimizers. So this is another picture of how QA/OA looks. This green box signifies one layer of the cost and mixer Hamiltonian, and you can pile up more layers in your quantum circuit to increase the expressibility of your ansatz. There's a proof that if you go to p is equal to infinity, you basically always get the optimal solution. But but industrial problems do not demand exact solutions, and they can do with approximate solutions, and so finite p works. But what exact p to use sometimes differs based on the problem that the industries are interested to solve. Moving on to the literature review, last 10 years, industries have used these NISQ algorithms to solve problems in various sectors. Starting with mobility, we have a quantum shuttle by Volkswagen. In this, there was a conference in 2019 in Lisbon, Portugal, a tech conference, in which the buses of those conferences were routed by a quantum processor in order to optimize for time, like basically minimize time to avoid traffic. So the quantum processor received real-time traffic data, and it gave as an output the route that the buses should be taking in order to avoid traffic. So this was, I think, the first commercial application of quantum computing. Moving on, we had in Industry 4.0, we have job shop scheduling, which has been solved various times using annealing and QA/OA and various algorithms, and is a famous problem touted to be solved with NISQ algorithms. Moving on, we have pharma and healthcare. In pharma and healthcare, a lot of classification problems like classification of non-small lung cancer patients, classification of dementia patients, and lung cancer detection have been solved using these NISQ algorithms like variational quantum classifiers. In the finance sector, we have portfolio optimization, which has again been tackled using algorithms like QA/OA or frameworks like annealing. So as you can see, there are already a lot of problems that have been solved using the NISQ algorithms. But a thing to note here is that these problems, when I say these problems have been solved, that is not up to scale of the industry. It's only up to a small scale. Like, for example, the tail assignment problem of assigning flights to particular aircraft to particular flights has only assigned up to 25 flights, or works for 25 aircraft, which is a very less number to scale with industry. And so that's a serious limitation that we face. But we currently work with a small number, and we have obtained speed ups from the classical algorithms, or at least a competitive performance. My problem statement deals with experimenting with these variational quantum algorithms and seeing if we can tweak them a little in order to tailor them for specific problems. So the problem I'm currently working on is a case study in the field of smart charging of electrical vehicles. This is a preprint on arXiv, and my initial goal is to reproduce the results from the above preprint. This preprint has two optimization problems, and using QA/OA mainly. So my first goal would be to reproduce these results. And once I've reproduced the results satisfactorily, I'll start incorporating more constraints and making the problem more realistic, and maybe maybe try to obtain an empirical lower bound guarantee of QAOA on maximal independent set problem. That's the goal for now. Once I'm done with this, my mentor and I plan to go on to these other studies and see if we can use maybe other quantum algorithms or tailor the current algorithms for these specific problems in order to get better performances. My progress so far has been sorry, yeah. So far, I have been I've mostly spent my time learning. So I started with attending some attending some conference talks. I did a quantum machine learning course. I attended some quantum machine learning challenges this one by Xanadu. So all this familiarized me with the current industry status and also various quantum libraries that were there, quantum computing libraries that are there, like Google Circ or PennyLane's Xanadu. Xanadu's PennyLane, Amazon Bracket, and IBM's Qiskit. So after all this research, I boiled down to PennyLane as the framework that I'll be using for my quantum circuits. This is followed by literature review. And finally, in the past 2 weeks, I've gotten to solving my problem, and the initial results have been satisfactory. I've been able to run a raw implementation of 3 algorithms in the paper, getting satisfactory results. I've also made some observations that are not typical, but have been noted in some other papers as well. So yeah, that has been my work so far. These are the references that have been used in this presentation. I'd be happy to provide them if required. And I'd like to end by thanking my mentors from the ED department and also at Bosch. I hope to continue this sort of work in the coming months and produce fruitful results. Thank you.